fortunate today to have Dr. Banavar Sridhar as our speaker. He is currently a principal engineer at the University Space Research Association, which supports NASA's Research Center in Moffett Field. He used to be a NASA engineer scientist, but he was not very productive, so they kicked him out. No, he actually, why did you just decided to move on, right?
Well, I thought I earned my retirement.
Oh,
and
okay.
you know.
Okay, so he felt that he earned his retirement, so he became, so he got another job, which is what we all do once we've retired. His research interests span many subjects related to aviation. Broadly speaking, they relate to the application of modeling and optimization techniques to aerospace systems. He's received about 1,000 awards, and he developed something that many of us have used over the years called the Future ATM Concepts Evaluation Tool, FACET, which received the NASA Software of the Year award, among other things. I guess I'll just leave it to you from there. Okay.
Thank you, Mark. Thank you.
So,
I don't know. Thank you, Mark, and good morning, everybody. And let me start. And you know, in Indian tradition, as we are talking about data science, we always like to have a teacher or a guru. So my first question for you people, I'll be talking about the applications of machine learning techniques to aviation operations. So you may want to think, who would be your data science guru? And while I'm talking, you can think about it. Maybe it helps you focus better. And towards the end of my talk, I will show who I thought would be a good person for the role. Okay, with that, so I started working at Ames at a time when helicopters were very important. They were thought to revolutionize urban traffic. We used to work on something called vertical short takeoff and landing. And there were all kinds of studies done. But two things, the ride in the aircraft and the noise, the passenger comfort and noise never made those very big vehicles a regular transport vehicles. But they always remained to be special class vehicles. And at Ames, we started working on something called automated map of the Earth. These are helicopters which fly above treetops. And here is a pilot who is very immersed in what his mission is. And we thought we would help him while he is flying the helicopter to see obstacles around him and display it on the helmet-mounted display. And is there a pointer? That's the light, right? Okay, thank you. So we had this vehicle. So we had these two cameras on board, and we had a big 36 parallel processor behind. And you know, we were flying, we were taking images, and we were doing onboard processing and say, well, here is an object, a truck in front of you 600 feet away or 1,000 feet away. And this was flown by both NASA pilots, Air Force pilots, and Army pilots, and was really the state of the art in object detection using cameras. And from then, we move to this picture today, which is again sort of a coming back of the same. This time the helicopters are smaller. They are with electric propulsion. They are quieter, more nimble, and we are thinking, and they are cheap. And to give you an idea of the cost differences, the hardware we were using at the time for doing the image processing was about $500K in the dollars at that time. At that time, you could buy a nice house in Mountain View or Los Altos for that price. And we developed all the software, the image processing software as the Kalman filter to find distance to obstacles more using that. Today, you probably can buy that kind of a package for $500 in today's dollars. So what has happened in between STOL and urban air mobility is there are many things that has happened both in the hardware and the software development, which has made newcomers into the aviation industry. People, the entry to aviation industry was very limited to very large companies, but now you have a lot of people who can get into that field from different areas. So this is where I feel machine learning and data science have a lot of promise, because in the development of tools to not only to manage the enormous amount of data, but you also want to provide services to these vehicles at a very low price. Because the current system we have in air traffic management was meant to serve few number of aircraft with people, and those are, you're trying to serve these vehicles which are costing in $50 million to $500 million range. So back from millions, you're dealing with vehicles which are costing in the thousands. So you have to provide service at a much, much lower cost than the way we are providing air traffic service. So that brings me with the background. What I would like to talk in the next 30 minutes would be, as we know that there is, everybody is applying machine learning to all kinds of problems. Especially, it has been very successful in predicting what you will buy in the next half an hour or this week. And we have several trillion-dollar companies in our neighborhood doing that. So what I want to do is, there is a lot of interest in machine learning, and how can we apply that to aviation operations? Where would it be most appropriate? And step back and say, you know, simulation and analysis methods are not new in aviation operations. And then take a quick look at physics-based way of modeling things and data-driven ways of modeling things, and see what the differences are, where the strengths and the merits of the different things are. And then use two examples from our work at NASA to highlight some of the problems, promises, issues in applying machine learning techniques to aviation operations. Obviously, this is a biased view, but, and then end with some of my thoughts. You know, the problems in aerospace operations, they cover a large, both spatially and temporally. You could have problems like you are trying to do conflict detection and separation between two aircraft, you're really sort of, that's a local area problem, could be a few hundred seconds. But on the other hand, a controller may be controlling aircraft in a sector, which could be several thousand square miles or several hundred square miles. And he has many aircrafts, and his span is 10 to 15 minutes. And then you have the traffic flow management problem. This could be, how do you make the aviation fly efficiently and safely in the United States, where you have thousands of aircrafts and you're dealing with 6 hours, 8 hours, perhaps a whole day. And then if you're thinking about what kind of an impact aviation has on the environment, whether it is noise or contribution to the global warming, you are really thinking of the whole entire globe. And you're also looking at the impact over hundreds of years. So the kind of modeling that is needed really varies what exactly is your task. So one of the points I want to make is, the modeling is really driven by what is the problem you're solving. And to me, most problems in air traffic management fall into one of these categories. It's like, if you have a hammer, every problem looks like a nail you want to hit. So I think of problems in air traffic management as either prediction of trajectories or classification of trajectories or optimization of trajectories. Within that class, you can frame most of the problems you have today. And as I explained, the modeling approach really depends upon the task. What do you know about the task from the past? Or what is the current status of knowledge in that area? And if we are going to use machine learning to advance, it really depends upon what data is available, or if the data is not available, and if it is a futuristic kind of problem, what would be a good way to synthesize the data in order to solve the problem? My picture on the right-hand side is to say, when aircrafts fly, the aircraft is assisted by an air traffic control center on the ground belonging to the airline. And then there is the FAA, which manages this aircraft to keep them safe, to keep them apart. And so it is this triad which makes air traffic work successfully. So I don't want to spend any time on machine learning itself in this, other than here, what we want to do is look at a lot of data, and based upon the data, look for patterns in the data, and that is our model. And having trained the model, you want to see how well it is able to work on similar type of data, or if it is a good model, can it generalize? And the kinds of techniques we have used at NASA Ames would be mostly support vector machine, decision trees, neural network, and reinforcement learning. And so here is my sort of a big view of where the strength of the physics-based models and the data-driven models are. Even in physics-based models, there are several different kinds of models. You can model every aircraft, or you can say, I will model the aircraft as a volume, and I'm interested in aggregate models. Or you can have linear models, nonlinear models, many, many different kinds. In the data-driven models, although it is a black box, the structure of the model will depend on the kind you're using, whether it's a neural network or decision trees. They provide, although they are black box, still there is a structure. And one of the advantages of physics-based models are when you get the result, it is easy to interpret. And trust is built upon your understanding of what the automation tells you. So that would be a big issue for data-driven models. How do you explain what you're getting? And on the other hand, model building the traditional way is very, very expensive. You need a lot of experts, a lot of understanding, takes a long time. So the data-driven models have the advantage with the power of the software and the computing available to us to be able to do it faster and perhaps cheaper. The suitability is obvious that, you know, if you have very good, well-understood physics model, you're not, data-driven models are not going to add anything to it, but you could still use the physics-based model to improve upon using. This has been done traditionally in guidance and control systems, in estimation or parameter identification. That's what parameter identification is all about. You have a physics-based model, you have lots of new test data, you improve the model. Now, feature selection is important in all areas. You know, this was recognized when people were teaching you, I have a collection of points, should you fit this with lines? Should you fit this orthogonal polynomial? Or sines and cosines, are that a good basis? They used to call them basis functions, but now we have graduated to features. That is still a major issue. That will either make the problem by the insight you have or the way you select, a problem becomes either very big or manageable. And size, having a minimal order model has always been valued in analysis. We always talk about minimal order models. And so you want to fit the data and not the noise. So the same problem appears in data-driven model, but it has different words. It's balance between overfitting and underfitting. They have several different techniques to balance it. So I'll talk about, there are lots of issues. So I thought I will take two examples which I am familiar. First, I thought I would do a survey of all the applications of aviation operations. When I tried to do that the last time, people said, hey, you know, it's too many, he did this, he did this, he did this. Why don't you talk about something you know very well and try to illustrate what the important features are. And so that's what I'm trying to do in this talk. And so we have applied I worked at NASA for 34 years. Over that time, you know, we have applied it in many, many different problems. So I thought I will take two examples where machine learning techniques definitely have an advantage and see how well they do. And so I try to focus on man-machine interaction kinds of problems. And also, we don't know, in a lot of very critical applications, it is not enough to say, this gives me a good solution 70% of the time. So I'm looking at problems where the risk of a bad decision is not a big problem. So in selecting the two examples, that was my criterion. And So the two problems I'll talk about is the estimation of NAS performance metrics. At NASA, we always say, don't use an acronym before you have defined. But I have fallen into that trap. NAS is National Airspace System. That's the collection of all the airplanes, the airlines, and or our national aviation system. So how do you establish? And they have metrics, things like delay, how many aircrafts are flying, and those different things. And it's on an application called dynamic weather routes. So why do we worry about performance metrics? Is there some way I can turn off the number there? Let's stop share. Oh, great. Okay, that may be a good location. So weather is a big problem in aviation. And generally, bad weather causes delays, which is an unpleasant thing. So the performance of the system is measured by how much delay trying to keep the air traffic system safe produces. So what we want to do in this example is to relate delay, cancellation, and all those things based upon the weather conditions. As you see in the picture, here is an aircraft going from San Francisco to JFK. It has its nominal route, which is shown by the green line here. And because there is convective weather somewhere, we plan to go around the convective weather, which increases your route length and may cause extra time. And also, the capacity at the airports might also add to the delay. Why doesn't it? Pardon? Oh. Let's stop for a second. And what you're seeing here is you see a lot of blue lines. Those are aircrafts which are in the air. They are arriving at 3 major airports in New York. So you have flights coming from the south, from the west coast. And what you will see is, they're all flying fine until the weather comes over the airports, which reduces the capacity of the airports. And this causes flight delays. And let me run that thing. See what's happening? That airport is completely swamped by bad weather. So the capacity at these 3 airports in New York is reduced, and these aircraft which are coming have nowhere to land. So they will have to circle or be in holding. This is what creates delay. And I'm trying to show you on worst possible days. on this particular day, so you are seeing delays, and those are all the aircraft which are flying. All my gray dots are aircraft which are flying on time. Everybody's happy on those planes. So the blue ones, the blue dots are delays anywhere between, in air traffic management, less than 15 minutes delay, like the class at Berkeley is supposed to start at 11:10, is not a delay, less than 15 minutes. So all the blue dots are aircrafts on that day which had delays between 15 minutes and 2 hours. And the red dots are really the unhappy people on that day who were delayed more than 2 hours. So this is the kind of data you have. You have the tracks, you know the delay. You know the delay. So air traffic collects a lot of data. These are stored in different things called OpsNet, aviation system performance metrics. For this particular work, we used traffic data from 2004 to 2008, traffic every day of those days. So you have the kinds of images I'm showing you are having for 4 years. And you also have the convective weather and the wind data for those. And so if you have this, so I want to use this volume of data to create a model relating delay to weather. So I'll have to make lots of decisions. What is nominal traffic? I will also have to say, what would be the appropriate things to select in this voluminous amount of data as to how I characterize it. And that would be my future selection. And then I say, what would be my modeling approach? So, this didn't happen over a day. This happened over several years. So, pardon? Yes, sir. Oh, wait. Which one? This days in 2006, that is the total delay of all the aircraft during that day. Yeah, that's the kind of data you have in OpsNet. If you go to aviation performance metrics, you get that hourly. So I'm plotting delay in 10,000 minutes for the entire year. And that's the bottom one is a histogram. So we came up, or there was an idea about weather impacted traffic index, which is a very simple notion. You have aircraft and you have weather. Where they are co-located, you're simply asking how many aircraft are affected by the bad weather. That's what VT is. You can compute it as a function every minute. You can compute it in geographical locations, or it's a very general definition. So you can have VT for each sector. You can have VT for centers. You have VT as a function of, VT is a function of time. So that was our feature. And so I said VT is the number of aircraft affected by the weather, X, and you can define it either for a center or at an airport or in many different ways. And the performance metric is I'm going to use that to estimate what the delay or cancellation is. The general idea is you have some idea of what the traffic tomorrow is going to be. And also you have an idea of what the expected weather tomorrow is. So if I am operating the system, I want to know tomorrow, what is a reasonable amount of delay to expect? If my delay turns out to be wrong, then I have to go and look why it went wrong. So it's like a very sort of a, like, you know, the thermometer or the temperature in your body to say whether the system is operating normally or not. So, so we want to estimate the delay or the cancellation. So we tried, okay, we know how to do linear regression, multiple linear regression in the sense that instead of using delay for the national location, we will estimate delay in all the 20 centers. That would be the multiple linear regression. And then we also said, well, let's build a neural network for this and see how well we can estimate delays. So, so the inputs are to the neural network would be, you can take the images and feed it directly. And you can go through convolution layers and pooling layers and all, and then get the features. So we thought it would be, this was when cloud computing, this was done about 7, 8 years ago. Cloud computing was not that easily available. So we said we will process them, store VT data, and that is what would be fed to the neural network. So the input layer is really the VT inputs, and our output layer is what is the performance metric, either delays or cancellations. So when we try to do that, you know, the neural network converged after about 200 epochs. And the neural network was very good in modeling the delay extremely well. And I can show you that in the next picture. Here is we trained it on the 2004 and 2005 data. And you can see that, you know, it's very well models. But when we tried to test it on 2006 data, it was not that good. The performance was not that good. So this is always a problem. You can very well fit the training data. It usually does not generalize very well. So we try to reduce the overfitting by several different techniques: early stopping, principal component analysis, stepwise regression, and Bayesian regularization. And in the interest of time, I'm going to move a little bit faster to finish this. So here you can see how the different methods did based upon looking at the cross correlation, as well as the root mean squared errors, as well as the average errors. So, you know, the neural networks, whichever method we used for the stopping criterion, did better than my linear or multiple linear regression. And this was true across whether we used OpsNet database or whether it was ASPM database, or we did many, many different variations of the studies. How did it perform in summer? How did it perform in winter? And all those things. That's one example. This is just sort of summarizing what I said. And the next example I want to talk about is what we call as dynamic weather routes. We have had a long project at NASA where for a long time we have had this idea that, you know, things do not get updated fast enough in the air traffic management system. We plan, and then the replanning is not fast enough. So an aircraft may be assigned a route to fly during the early part of the day, but the weather is always the predictability of the weather, exactly the location where it occurs, is very hard. So the weather might have occurred in a different place, but this guy keeps flying the old route. So we have this system which sort of looks at every aircraft in the United States and looks at the path he's on and constantly checks, is there a route he can fly, which saves him time, okay? And if it does, and it also looks at a lot of the different constraints for the new route. And if it does, what it does is it tells an airline coordinator or a person at the airline on the ground to see if that is of value to the airline. If that dispatcher thinks, yes, saving 15 minutes is good in terms of fuel savings, but it will not affect other parts of our operation, he may ask the pilot to say, hey, go and request it. And if the pilot requests it, and if the controller says yes, then the aircraft would take the new route. It's the way it is implemented is kind of tedious, it is long, but that's the state of our current air traffic system. So we want to make these automated decisions faster and faster and make it smooth. So we developed this at Fort Worth Center in 2012. Here is what I was trying to say. Here is a aircraft. Here is his nominal route. And the green one is the original flight planning route, where he is going to Denver eventually. And so the air traffic or the DWR says, hey, you can go to this fix in a shorter time, and you need to follow this route. While he's doing it, it also says, if you do this, you're going to save 24 minutes. But while doing it, it's also doing a lot of other calculations. Here is the route taken by the nominal aircraft. And these are the sectors through which he goes. A red sector means he is going through a sector which is overloaded. And so he was already going through some difficult sectors. This is the new route which has been suggested. So along the way, it checks every possible sector. And this seems to be, and then, it doesn't, not only it tells him how much time he is saving, but he also provides the dispatcher as to what kind of congestion the new route may go, and what was the kind of congestion through which the old route was going. So it gives him not only the savings, but also gives the dispatcher the situation awareness. Which one? This one? This is, I would say, 500 miles or 1,000 miles. You're going from Dallas to Denver. Yeah. My aircrafts are way big, so. Yeah, it's Texas to, okay, yeah. So, we had this for many years in American Airlines, and we tested it on their regular flights from 2013 to 24. Most of the time, American Airlines was also worried about some personnel trying to manage this, and a lot of times they had nobody there. So like I say, more than 3/4 of the suggestions made were never even acted upon because there was nobody looking at the screen. And when they were looking at the screen, they accepted 65% of the suggestions that were made. And out of the 65% of the suggestions the dispatchers accepted, the air traffic controllers accepted only 38% of the. It's like carrying water in a very leaky bucket. So the idea was, so this is a good problem to understand why are the suggestions made not approved by this combination of people, and what is influencing their acceptance rate, and is it possible to tell them or give them fewer suggestions or suggestions which they are most likely to act upon. So this is where we thought, the traditional way would be we would go to talk to subject matter experts and ask a lot of controllers, why are you not doing this, or what is in your task that you would like. So we did that also, but then we thought, well, maybe here is some place where machine learning techniques, which a lot of data collected, might provide us additional guidance. I probably have to speed up. How much time I have? 5 minutes? Okay. So here is all the routes which go from one of the centers in DFW, sector 48, and those are all the routes which are going from this location, ADM, to Albuquerque. There are many, many routes, but out of those routes, only some routes are used very frequently. You can see it. These are the various routes that are possible, and one of the routes is used 526 times, and the others are used less frequently. And what we found was the acceptance rate of a route is higher if he already, it's like, you drive by 101 all the time, so that's your favorite route. If somebody says, take 101, you're happy. The other alternate, you don't consider. So the 96% of the accepted routes were the ones which are used very frequently. But just because a route is accepted frequently does not mean if you make that suggestion, it will be accepted. It's necessary, but not sufficient. Okay? So this is how we would have done it. So we tried to see, can you tease this out of the data? Or can you see tease out the factors that make the acceptance possible by looking at the data? And so we had all this air traffic or the dispatcher acceptance data collected. And out of these, we had to go select features or extract features from the collected data. So we had 544 observations at American Airlines from 5 months of testing. And so, these features obviously would be sectors where the aircraft is there, how busy it is, the sectors through which they are going, how busy they are, and if you give a deviation, how far the deviation is from the original route, those kinds of things. Based upon all that, we came up with these 7 factors as the thing we should use in the machine learning algorithms to fit the data. And these were the features that were selected. And we used 5 different methods. One was logistic regression. The other was decision tree, and then support vector machine, random forest, and ADABs. And we use the kinds of metrics that are used in machine learning algorithms as the way to test them. And if you looked at, I'll just focus on the F score, of the 5 different algorithms we use, the random forest appeared to perform best. And so we did a lot of tests on the random forest. How many trees are optimal, whether it should be 20, 30, 40. And also, for this set of data, the tree size of 40 seemed to maximize the F-score. And then we did, for this particular model, we did a lot of cross-validation, tenfold cross-validation. And the F-score is not that much different. Oh. The F-score for the test set is not that much different from the F-score for the training set. So that's my last slide. And so that's the challenges in applying machine learning techniques is the availability of the training data. And the feature selection is an important factor that will affect how much computation time is needed, whether you are even successful in solving the problem. And there are many, many learning methods available. So one good thing today is you don't have to write all the software. So you are already at but you still have to understand what is the guiding principle of the software or the theory behind the software. And like I said earlier, there is no single algorithm which is best for all tasks. You may be able to say, if you are trying to say how much is the delay, maybe one algorithm will perform much better than saying, when you ask the question, what percentage of the time is the delay going to be exceeded? So there are different questions, different algorithms might perform differently. And we talked about the balance between overfitting and underfitting, and also evaluating the model itself. And I think I've said all these. I tried to give you a flavor for where machine learning techniques could be of value in aviation operations. It has a big advantage when you don't have models. And I said about one of the things I think is, if you're trying to use it for a very critical task, you still have to take a good look at that machine learning technique. And I talked about the task, the prior knowledge and data. That is the key to your modeling approach. And so here is my answer to the first question I posed. You may have had different people in your mind. I thought he would be a good person simply because he was obsessed about observations. And until he came, everybody was fitting this data of planetary motion with circles, wrong feature, right? And he said, hey, let's use ellipses. And he said, we'll have the sun at the foci. And a lot of data suddenly became science. So that's why, there are other great people, but I thought he may be a good, and also there were nice pictures of the planetary things on our website. And it's very hard at NASA to put any of these pictures unless it is publicly available, okay? So that was another choice. I could put his picture without any, So here is my talk. I will be happy to answer any question. Yeah, there are two things. A lot of the literature is about supervised learning. with unsupervised learning, two issues. Suddenly, the amount of computation you have to do becomes very large. And so I don't have the reinforced learning. To me, in very early days of guidance and control systems, people used to do adaptive control. It never took off because the amount of computation available, so it's a balance. So if you can do labeling, obviously unsupervised learning, learning without a guru is hard because you may wander in different directions, but you may find something very valuable also. So I don't think there is any sort of a, this works here or that works here to me. You have to be really guided by your problem, your understanding of it, and then maybe the good guru is not available, so you will have to be self-taught.
So even in unsupervised learning, okay, you have to have some notion of the the basis for the classification.
Right. You have
so
to
for
have
example,
a reward or
yeah. So you have to say, for example, if two things are separated, you have a notion of a distance, then you can use classification to say this is below this distance and that is above that distance. So nothing in that sense is completely unsupervised, right?
No, I think the advantage is you have to have a notion of good or bad, right? That's you have to have, but you don't have to say this falls here or that falls here. But in some ways it is, you have a 0-1 kind of classification, even in the unsupervised learning.
Going back to some of the stuff you're talking about where you use the training data set, right? Mm-hmm. And you compute certain performance metrics and you predict this is what's going to happen for the weather part especially, right? Mm-hmm. And then in future, you actually know what happened.
No,
So let's say you predicted tomorrow this is the best route.
Right.
Mm-hmm. And you see actually what the aircraft did.
Right.
Right. And you can test how closely you match because now this data is itself trained,
sure.
Right?
You can always do that. Yeah, you can have a continuously updating of your algorithm based upon that. That's what recursive methods are, right? Or that's what a Kalman filter does, right? You have so recursion builds upon that idea that I have the model, I get new data. So there is another thing also that you have to worry about in these things. Between 2004, let's say you built on 2004 to 2006. In between, none of these systems are stable or fixed. There are continuous improvements taking place. So it's never perfect. What you're asking for is how reasonable are you? See, the predictions can go wrong for many reasons, right? One is the weather prediction could be horrible. That's why you got these bad delays. Or your operations planning was terrible. The weather materialized where it was supposed to, but you made bad judgment in how you planned. So it could be one of the two.
So Banavar, what made you guys conclude that it was overfitting versus it did not have the adequate number of features, or there were important characteristics that were missing that would have been a better generalizer of the future?
No, but just the simple fact that, when you reduce the size of the model, it was able to generalize better. So that is what the higher level model. Take the simple example of if you have 100 points, and you're trying to fit with a large number of lines to fit that. Okay, then the noise in the data drives the model. But if you say I'm going to use fewer and fewer, and the data, not the noise in the data, which is, it is possible that another set of features could have solved the problem much better. For this, okay. So you have to settle on several different things, right? You have the choice of a model, that is, a whole collection, and then you have features. Whether we could have chosen the wrong features. That's possible. There could be another. See, that is where you will have a lot of problems when people say, I have all the data, I don't have to know anything about my problem, okay? And I will solve it. That does not happen in realistic problem where you have spent a lot of money on things. People don't build without understanding. So that is, but in some cases, maybe it is not possible, and especially if it is a collective aggregate behavior kind of thing, probably these models are they're very successful. There is no question about it, right?
Is there some questions on NASA end? At NASA?
Yeah, I have a question, sir. This is regarding one of the earlier slides that you differentiated the physics-based versus data-based models, and actually categorizing the models, in the various manners. I was just wondering, how come complexity never came into one of those categories? You had the size, you had many of the other parts, but I didn't see.
So I did not include complexity as a thing because we are trying to apply all this to real air traffic management, which has all levels of complexity. What I tried to say was, in all modeling, you should always attempt to go for the minimal order model. That's where the elegance are, trying to find a simplest possible solution. Without question, all these models are complex. You're dealing with thousands of aircraft. That's where the spatial temporal range, that's what makes the problem complex. What makes the problem complex is you have machines, you have people doing decisions. In air traffic management, we have hundreds of controllers looking at that. They make decisions. Thousands of pilots are flying. They make decisions. And the overall performance of the system depends on the combined actions of many, many actions taken by all these people. We have modeled it in so many different ways. We have papers trying to show what would be the best network to represent these things. So there's only so much you can say in 45 minutes. Uh-huh. Thank you. I can have a conversation with you tomorrow.
Okay.
Thank you, Banavar.
Thank you.
Thank you.
Thanks, guys.